everyone. So first, let me thank the organizers for such kind welcoming. And for 15 minutes, I'll put you to optical astronomy, and then we'll come back to the radio. Okay. So let me first say a few words about SNAD project. SNAD is a project devoted to anomaly detection in astronomy, in astronomical databases and catalogs. Before I'll move to my talk, there is a very important question. What is anomaly? What do we mean by anomaly? And there is human definition and there is a machine definition. So machine definition is rather simple. So you have your data, you describe your data somehow, and in your parameter space, let it be just y and x. All normal data will be clustered in, let's say, several regions. Here it's N1 and N2, and all anomalies, outliers, will form smaller cluster or just will be separated somewhere. But what is an anomaly from the point of view of machine is not necessary astrophysically interesting objects. The human definition of anomaly is much less defined because what is interesting for me as a supernova person is not necessarily interesting for the variable people, for example. So, but generalizing, we can say that everything that is astrophysically interested or rare or completely new, we could call an anomaly. In our project, we are using the so-called active learning pipeline. What does it mean? So we described our data. In our case, these are light curves with some features. And then it's all go to the machine learning algorithm. Well, doesn't matter which one here. After it, all the objects will be ordered by the so-called anomaly score. And we select top 10 or top 20 candidates, and they go to the experts. So they must be visually inspected by the expert domain. And I would like to stress that if you use machine learning, this part is super important. So we should not use machine learning as a black box, and we must check the objects, the results that we have. And after this step, experts decide, is it interesting, very interesting, not interesting. Then this feedback goes back to the machine learning. And this loop repeats till we find something very interesting. And, well, very interesting objects. We can organize some follow-up observations, publications, etc. One of such approach that we use is called active anomaly discovery approach. So this is an isolation forest as a machine learning algorithm, and then some humans that at each step of the algorithm, at each loop, provide some feedback to the algorithm. And then some weights recalculated inside, and the model changes. So here you could see the results, let's say some quality check of the algorithm. This is a fraction of anomalies for some synthetic data and for some real data, depending on the number of candidates of the outliers. And the green line corresponds to this active anomaly discovery and provide much better results than static or simple isolation forest algorithm, which is orange, or some random samplings. Interesting output of such approach is that this algorithm can be used as a targeted transient search. And it's what we did in this work. We used Zwicky Transient Facility data to search for supernova in data releases. It resulted in 100 supernova-like transients, and half of them were known before, and another half were missed by the official alert stream for some reason. Here you could see one of the examples. As you can see, very nice supernova light curves with a lot of data points, but for some reason it didn't go through the ZTF alert pipeline. And of course, we should not miss such cases in the future, especially for LSST. A few other examples. Unfortunately, since we were looking for the supernovae in data releases, so in archival data, we could not come back to have some additional follow-up observations. So, but we have to classify them somehow. That's why we used some simple models of different supernova types to classify them all. Well, we could call that a kind of photometric classification. And some unexpected discovery of this classification was a discovery of a few superluminous supernova candidate. One very promising and interesting, we call it SNAD 160. This is this pink curve in comparison with the classical light curve of SN 2006 GY, which is also superluminous supernova. This one is much broader. We did some hydrodynamical modeling and estimated progenitor mass to be about 250 solar masses, which makes this object to be a perfect candidate for pairing stability supernovae. So this is a very nice result. During the supernova search, we found some other non-catalogued objects, so I listed a few of them here. This one, some non-catalogued active galactic nuclei, or some very fast flares like red wolf flares with a kind of complex shape. The study of such kind of event is very important for study of habitability zones of the stars. Some non-catalogued eclipsing binaries, etc. During our last workshop this year, we also discovered a binary microlensing event in ZTF data. You can also notice that in ZTF, despite of the standard cadence of 2 days, there is also high cadence survey data. So in this data, we basically found our M-dwarf flares and this binary microlensing candidate, some optical counterpart of radio sources. And in the end, let me promote a little bit our SNAD ZTF Viewer. This is a very efficient tool to work with ZTF data. So because it allows you to cross-match different ZTF IDs that belongs to the same object, different passbands, different fields. There is a cross-match with many other catalogs, so summary, coordinates. You can also download the feeds files for each of these points. There is Aladdin map and many other tools that can be useful if you are working with ZTF data. Yeah, and just the slide before the last one, among the anomalies that we discovered, there are plenty of artifacts, and we even created the SNAD artifact catalog. You can find much more amazing images there, but well, you could see that some of them reminds, I don't know, alien spaceships, etc. And in conclusion, let me repeat that, well, in real data, there are a lot of artifacts, and this is one of the lessons we learned while working with big data of ZTF, and definitely some additional approaches are needed to clean up the data, especially when you're looking for anomalies, because in our case, well, 80–90% of the candidates that we check are artifacts. Then active anomaly detection that includes human in the loop is very important in such kind of studies. And in our supernova search in the TF data, we found around 50 new candidates, which is probably not very important for supernova science, but it's very important again for LSST survey and for other survey. It means that there are some gaps in our pipelines, so we should not miss such kind of transients in a future alert stream. And anomaly detection system must be built for the experts. So before you start anomaly detection, you have to know which kind of anomalies you are looking for. Thank you.